Continue. Okay. All right. So the remainder of this will be recorded and I can post that somewhere. I don't know where I'll post it. I'll probably post it on my YouTube channel. And then you guys can go there and subscribe to me and watch this lecture. Okay, so that is okay. So let me just I'm seeing the questions coming in, and I'm just okay. So I see a question from Paul. I'm going roughly in order here. Again, if I miss your question after a while, just repost it if it scrolls away. But I see a question from Paul. If we want to find the nth root of a number. Okay, so here's this question. We're trying to find, let's just take the same number. Now imagine us trying to find the nth root of a number. Oh, the fourth roots of this number. He's asking this question, can we leave it in the form e to the I theta plus 2 pi k k equals 0, 1, 2, 3. And no, I think that is not a good idea, right? Because that is this is not showing that you actually totally clear where all of the roots are and simplifying, and it would for sure not be adequate if it was asked for a rectangular form. Okay, so let's just talk about how we would find this fourth root anyhow, and then what I would expect you to write down. Okay, so let's just take that same number. We already know this number. Okay, so definitely if you're trying to find a fourth root like this, you're gonna want to be moving to polar coordinates. This would be really hard to do in rectangular coordinates. So I mean, let's forget, I don't even want to go into how to do it in rectangular coordinates. I don't want to confuse the issue. So if you're trying to find nth roots, you're gonna need to convert the number to polar coordinates. We've already converted this number to polar coordinates. We know that it is root 2 e to the I minus pi by 4. Okay, at that point, what you want to do is rewrite the number, like as Paul was indicating. So we have this number z, and now what we want to do is find z to the 1/4, right? That's our goal here. So what we're going to do is we're going to take the number and we're going to rewrite the argument minus pi by 4, and we're going to add 2 pi k. Okay, so what we're doing is making the argument such that we can divide it by 4 and get a bunch of different principal arguments. That's the goal here. So we're adding this. This does not change the number. Right? Each one of these numbers, no matter what the value of k is the same position in space. So we do that, and then we take the fourth root like that. Okay, that means we'll take the fourth root of the modulus. So that will be 2 to the 1/8. And then we'll be like this, e to the I, and we'll be taking the fourth root here, minus pi by 16 plus pi k over 2. I'm taking 1/4 of minus pi by 4, and I'm taking 1/4 of 2 pi. And then we're taking a fourth root. A fourth root, when there's 4 of them, we know that it's a fourth root, there is going to be 4 of the roots. That's the fundamental theorem of algebra. Okay, an nth degree polynomial has n roots factored over the complex field. Okay. So now we're here. Now, what I would expect in this question is you would then say, okay, so we're looking for z to the quarter. We would say maybe, root number 1 is going to be 2 to the 1/8 e to the I minus pi by 16. Root number 2 is going to be 2 to the 1/8 e to the I minus 2 pi by 16, pi by 16 plus pi by 2, like that, or 3, like that, etc. 2 to the 1/8 e to the I minus pi by 16 plus pi. That's k is, this one here is k is equal to 0. This is k is equal to 1. This is k is equal to 2. And then the fourth root will be this guy here, e to the I minus pi by 16 plus k is equal to 3 pi by 2. That's k is equal to 3. Okay, so we then have all 4 roots written out. If the numbers are somewhat reasonable, you could then, convert this into a single fraction. This doesn't look to be too hard to do, so that, you can common denominator of 16, you could then convert to a single number. And then should you be asked for it in so this would be the answer in polar format. And then if you want it in rectangular format, then you'd have to go through and take the cosine and sine of each one of these angles separately. Like you would have to come here and say, okay, R1 is 2 to the 1/8 times the cosine of minus pi by 16 plus I times the sine of minus pi by 16, like that. And then these things here, at this point, you would not be able to get that out without a calculator. So you would leave it like that. This would be in rectangular format in calculator ready form. So that would be that would be the answer to that question there. Let me just keep going down on the questions here. Okay, so Yu Kwan has a question. Will we be able to factor polynomials with complex roots, say a quintic polynomial? No, and generally speaking, no. So I mean, what do we have? We are sometimes factoring polynomials to answer some of these questions about complex numbers. So clearly, I mean, if you have this ax squared plus bx plus c equals 0, you should be able to factor that with the quadratic formula. If you have a cubic, ax cubed plus bx squared plus cx plus d equals 0, you may need to be able to factor that, but it'll be such that you can guess the linear factor, like the root will be like 0, -1, -2, something like that, where you can see easily. For example, a cubic like when is this going to come up? There's a cubic polynomial that comes up when you're trying to find the cube roots, right? And then it's really easy to see that x3 is a factor here. So then that x minus 3 is a factor. So then you can use polynomial long division to find out what the quadratic is, and then you can use a quadratic formula to get the other two. And then the idea is to have in your head is that complex roots, which means the factors that have complex numbers, complex roots travel in pairs always. Okay, you're never going to have from a polynomial one complex root. That will not happen. Okay, they always travel around in pairs. So you would expect on a cubic polynomial, you're going to expect to have one real root and two complex ones. That's a possibility. So let's just because we mostly have dealt with quadratics. Okay, so I just want to say this. If we're dealing with a quadratic, what are our possibilities? Two complex roots, and they'll be conjugates of one another. There'll be two complex roots, or there'll be two real roots. There's never going to be like one complex and one real. That will not happen. Okay, so you've got those are the two possibilities on a quadratic. On a cubic polynomial, you could have three real roots. That's a possibility. You could have one real root, and that's possibility one, and two complex roots, and they will be conjugates. Two complex roots. Okay, that's the only two possibilities. You cannot have three complex ones. That won't happen. Okay, so that's the maximum of our factoring. For sure not gonna ask you to factor a fourth or fifth degree polynomial. This is not a course on how to factor polynomials, which actually in fact is a hard problem. Okay, so there's that. No, so here's a question in the chat from Gladys. Would cos pi by 4 plus pi by 3 be considered calculator ready? No. No, it is not, because there's pi by 4 is like 45 degrees. You should know, you should be able to use the two special triangles and figure out what is the cosine of pi by 4, right? So the ones that you should know, you should be able to get out of your head: cosine of 0, cosine of pi by 3, cosine of pi by 4, cosine of pi by 6, cosine of pi by 2. And then that's in the first quadrant. And then if you rotate the whole thing into the second quadrant at all those angles plus 90 degrees, you should be able to get that at all four quadrants, right? And so that's both of the ones you asked there. So no, so we should be able to go with the basic ones that are from those two special triangles, as I was saying in the beginning. You should be able to get those without a calculator. 6.1 is not on the midterm, right? We save the joy of the eigenvalues and eigenvectors for the final exam. Okay, 6.1 is not on the midterm. Okay. Oh, okay. So Aitan has a question. How would you solve a matrix for x when x appears on both sides of the equation? That's a good question. We haven't really spent that much time on that, but we, in fact, should know how to do this. So let's just say we've got some matrices. I'll just invent something here, and we can see how this goes. So I've just got a couple of other questions about the coverage on the midterm. So I have sent out, I think, actually 2 announcements about this, and we've discussed it in class, but I will repeat that here. 4.6 is not on the midterm. We're not covering section 4.6 at all. We've decided not to bother with 4.6 this semester. Okay, so that's gone completely. Won't be on the midterm, won't be on the final exam. The midterm is covering everything up to including section 9.1, which is the complex numbers. And so that's all of chapters 3, 4, and 5 plus chapters 9. And then I've reiterated this many times. People are like, well, what about stuff we learned for the first midterm? It's like, okay, but some of the stuff we learned for the first midterm we are using to do these problems. So it's basically comprehensive coverage in the sense that, you have to be able to do Gaussian elimination, right? I'm not going to be able to do anything without Gaussian elimination. And we learned that before the first midterm. So that is clearly still covered in the sense that it's required to do some of these more complex problems that we have. But I'm focusing on the new material. There was a correction to that announcement, 9.2. We're not covering 9.2 at all. What I accidentally had meant, yeah, exactly. I had meant 9.1b. So there's 2 lectures. There was 2 lectures on section 9.1 on the complex numbers. I meant that both of them were covered. I accidentally wrote that as 9.2. It is not 9.2. It's 9.1, 2 lectures. Yep. Okay, so now let's, where was it? Oh, here. That's back that items question, then I'll answer some of those other questions. Okay, so let's just pretend we have some matrices, A, B, C. I don't know, something like that. And then maybe better have 4 of them. So these are all matrices. Okay, we've got 4 matrices, and then we get some sort of matrix equation. I don't know, A squared times B is equal to B times C times D. Let's make it even more complicated. Okay, we have this, and then the question is something like this: solve for B. All right, this is, honestly, this is a similar question to something like this. Let's just put it into a format that you might be more used of. X squared y is equal to, z y w, right? Solve for z. Solve for y. Right? Exactly the same question. In this case, if I was here, let's just look at what we would do here in the numbers. I would move everything with the y. I'm trying here, now I'm here, I'm doing the equivalent, solve for y. You should see this as the same question, except we're going to talk about the main important thing to be careful about. Let's just say I was here, I would move everything to do with y onto the left-hand side like that. Right, and then this would be what I would do, and then I would be able to factor out the y, and I would be like x squared minus let's see, zw like that, and then I would be, that's equal to 0, and then I would be able to say, well, I guess in this case it's let's just like that. The whole thing doesn't come out to be 0, and then I would go like this, and okay, I would now have solved for y. And at this step right here, I would be very careful to say if x squared minus zw not equal to 0. Otherwise, this doesn't make sense. Okay, so if ever I divide, I am going to indicate that the solution subsequent to that is only valid so long as what I'm dividing by is not 0. Okay, so there's that. So I'm going to do exactly the same thing over here with the big exception. Okay, we do not divide with matrices. Okay, and so there's 2 things. Okay, there's no division, with matrices. Okay, so I'm thinking instead of multiplication, multiply by the multiplicative inverse. That's something to keep in your head. And then more importantly is you must remember that it's not commutative. Okay, multiplication is not commutative. That is a key feature. That is a big idea. not computed. That's the matrix multiplication. It's easy to sort of remember that in sort of vague terms, but then when you go to solve a problem, you see symbols and you just start using them the same way as your other symbols, and then things go badly quickly. Okay, so it's not commutative, and we are going to multiply by a multiplicative inverse. So in this case, were I to want to solve for b, I would be here like that, and I'd be like, okay, I need to say b equals something. I then have to figure out how to get the b by itself. So I mean, the first thing I'd be thinking is maybe I can isolate this guy. So then I would think, okay, how do I do that? Oh, I would have to then multiply on the left by the inverse of a squared, because that thing there equates to I. And I would have to do that. Okay, so I'm going to write it below, actually. I'm going to then multiply on the left like that. Okay, I'm going to multiply on the left by a squared. Then that is one. Oh, sorry. Let's get the other a squared there. A squared b. Okay. Then this thing here evaluates to I. So at this point, I guess I'm here. This may not be the most efficient way of doing this problem. Okay. And then I have to think to myself, okay, I've now still got b on both sides. So I need to be able to get, the b on the another thing here to say, if a is invertible. Okay, not all matrices are invertible. So this step not valid unless a has an inverse. So as soon as I make that step, I'm like, this applies when a is invertible. Okay, so then I'm here. I'm like, okay, hang on a sec. I need to be able to factor out b on the other side. So let me just show you what I'm going to do here. I'm going to multiply. Let's see. Okay, let me just go here. B minus, like I would do here, C, B, D. Okay, that's equal to 0. Okay, I'm wondering then how to get out. Let me put here plus a as well, just to make this so this is. I don't want to have it equal to 0. So this will be a. I'm multiplying a to the minus 2 times a, and that is a to the minus 1. Just added that here. So then this is equal to, I'm here. Okay, now I somehow have to factor out this b. So the first thing to know is if I have like this, b minus bc, and I want to factor, then what this looks like is this. Okay, this is different, right? I'm thinking when I'm going to factor with matrices, when I'm going to factor out this b, I'm thinking that b as actually b times I. So when I'm factoring it out, I am left with the I. So then I'm here and I need to factor it out, but I need to have the b in the same location at the end in both things. So I would multiply here by d to the minus 1. I'm multiplying on the left everywhere. I'm multiplying on the left. Let's multiply on the left. Sorry, let's try that again. Stop, pause. I want to multiply. I'll change the color. I want to multiply here, d to the minus 1 on the right, actually. I'm going to do it in the next line down. I want to multiply here, d to the minus 1, d to the minus 1, d to the minus 1. I'm multiplying through on the right in this case. So I'm like b d to the minus 1 minus a to the minus 2 c b equals a to the minus 1 d to the minus 1. And I still need to get the b in the same location so that I can factor it out. Let's see how I can do that. I may have made an example that's hard to do. Just a sec. All right, I'm gonna pause this example here. Yeah. So I think I concocted an example where it may not be easily possible to do. This is the problem with concocting examples on the fly. But basically, let us start here. Thanks, Paul. Let's just start with an example that's easier. Let me just have a situation where let me just fix my example. I'm going to make an easier example. A squared b is equal to c d b plus a, there, like that. Let me make it like that. I've just reversed the order. I'm starting a new, this is a new example. Let me just fix this. Okay, so then this question I would be like this: a squared b minus c d b is equal to a, and then I would factor out in this way a squared. I would factor out. Yep, I would factor out the b on this side, and this would be a squared minus cd. The key point here is that the b is on the right hand side. I cannot put it over here. That's not going to work because I'm multiplying it on this side. And if you see I'm distributing, I've got back where I am. And then I'm here. This is now equal to a. And then here I can simply take b is equal to a. And then I can multiply this by a squared minus cd to the minus 1. Okay, the inverse. Okay, yeah, so it's possible for, I guess, me to concoct an example like I did where it's not possible to do this, but the basic steps are in the simpler example are as shown. And then the key thing is when you factor, if you need to, you introduce I in this manner for this kind of a factoring thing, and you never ever change the order in any way, shape, or form when you're doing the algebra, because it ends when you do that. Yeah. Okay, let me just scroll down here on the questions. Okay, so here's a question from Sloan, which is a good question. Why do we use, here's the question. Why do we use the row reduced echelon form of the matrix for the row space, but not the column space? Okay, so let's just concoct some sort of an example where, and it is important. So this is a bigger topic. Let me just say a couple things about it. I mean, we spend quite a bit of time about this, and so if we have a matrix A, let's concoct some matrix A: 1, 2, 3, minus 1, 6, 4. I don't know. Minus 2, 3, 0. Okay, there's a 3 by 3 matrix. Let's just call that guy A. Okay, so there are the matrix A can come to us in various guises, right? This could be the coefficient matrix of a system of linear equations. That's how we first figured out that we could use matrices, right in the beginning of the course. So it's a possibility that these are the coefficients of 3 homogeneous linear equations. That's a possibility. Or I mean, there even could be a right hand side b, like it could be coming from a problem like this: ax equals b. Okay, this could be a matrix that is, we're thinking of it as an operator, which means that it does something like rotate or reflect all the vectors that you multiply it by. That's like more like what we saw on the computing assignment. So regardless, if we get one of these guys, a matrix, we can think about it abstractly, divorced from however it came up. Okay, so the idea here is, I just saw a comment here which is correct. Let me just, I multiplied on the left. I did it wrong. There, it's so easy to do that. Okay, that's a correction right there. Thank you. Okay. We have for this matrix 4 fundamental subspaces, and they are subspaces. They're not a subset, they're subspaces. Okay, and that is the row space of the matrix. That is equal to the space spanned by the rows. Okay, and then we have the column space of A, and that is the space spanned by the columns. And then we have the null space, and that is the space of vectors for which AX is equal to 0. Okay, and then we have the least used, the null space of the transpose. Okay, this question is about the row space and the column space that's been asked here in the chat. Okay, so first of all, the row space of A is equal to the span of the rows. I mean, that's what it means. So I could write it like this. That's row 1. That is the row space, right? The space spanned by the rows. The column space is the space spanned by the columns. Okay. All right. Now, the thing of it is, if I just write it like this, I write out the row space, and this is a correct statement, right? I have written out the row space, and I have written out the column space. If somebody just asks me, what is the row space? That this is a valid answer. Okay, but what we don't know here is what the dimension is, because how can we tell that? Because we do not know if these vectors are linearly independent or not. So, I mean, in this case, the dimension of the row space or the dimension of the column space, because we don't know either one, we don't know whether the dimension is 1, 2, or 3. It's one, it's one of those, but we don't know which one. And that speaks to the linear independence. Okay, so the typical thing to do is to row reduce this guy. Row reduce it. Let's just say we get something that looks like this: 1, 0, 1, 0. I don't know what this row reduction looks like. I'm making these numbers up. Okay, looks like that. There. Row reduces like that. Okay. What does that tell me? I mean, what is, in this case, what is the dimension of the row space? 2. It's 2, absolutely. And what is the dimension of the column space? 2. 2. No, it's not 1. It's 2 because we have 2 linearly independent columns. Okay. What is, I think the person who answered, Mackie, you might have been thinking, what is the dimension of the null space? So let's answer that question here. What is the dimension of the null space? No, dimension of the null space, not 2. It's 1. Dimension of the null space is 1. Okay, so let's why is that? Because there is one free variable, right? There is here x3 is free. So if I was to get this matrix and apply multiply it here like this, I would find that I would get a 0 no matter what was in the x3 column. So the dimension of the null space here is 1. There's one free variable. And then we have that one important theorem. Okay, that make sure that you know that one important theorem. That is that the rank of A plus the nullity. Nullity is the dimension of the null space. So the rank of A plus the nullity of A is equal to the number of columns. There's a rank nullity theorem. Yeah, if you remember the name of the theorem, it's not too hard to get it out of your head, right? Rank nullity theorem. Okay. So then the question is, if we row reduce, the original question was when we have the matrix in its row reduced echelon form, we know in this thing, we know that we've got 2 linearly independent rows. And if we want to know what is the basis for so now if we want to know what is, like, here's the basis. So we want to have 2 basis vectors for the row space. The basis for row of A, that is going to be equal to, and it's the first, I use these guys here. I'm going to explain why it is in this case. I'm using these two guys here. That it's going to be this 1, 0, 1 and 0, 1, 0. Okay, I'm using the rows from the row reduced echelon form. And if I want to know what is the basis for the column space, of A, I'm looking at this and I'm like, okay, these are the two linearly independent columns. And then I use these numbers here. I do not use the two columns from the row reduced echelon form. I use the two columns from the original matrix. Okay, so I'm here, and that is going to be here, 1, minus 2, 1, 1, like that, and 2, 6, 3. Okay, now this problem that I'm doing here, this is all of these statements here are only correct if this is like that, which it probably isn't, right? I just made this up. But assuming that this matrix A here has this row reduced form, then these statements are all correct underneath. And the question that was originally is like, why would I use from the original ones the column space and from the row reduced echelon form for the row space? Okay, so now let's think about what happens. The reason for this is let's think about what happens when we're doing Gaussian elimination, going from this matrix down here to this matrix. Okay, we're doing Gaussian elimination. We swap rows. We might have swapped rows. If we swapped rows, then this row here does not correspond to this row here. It may not, because we're allowed to swap rows whenever we want. Okay, so when we're asking for the basis, what we're doing is we have here, this is a row equivalent matrix. So we need to take the row vectors from the reduced form. When we are going on doing the row reduced Gaussian elimination, we never swap columns. We don't swap columns. And further, this is not a column equivalent matrix, right? We never say that. When we do Gaussian elimination, we always get a row equivalent matrix, right? We're not, there's no concept of switching columns and doing column operations. It's all about doing row operations. And so we need the columns from the original. Okay, so this way, this guy here, even though it doesn't look the same, this guy, should these numbers be correct that I just invented, this guy will span the same space as this. And this guy will span the same space as this. In the question of the column space, all we've done is eliminate the linearly independent column. Yeah, so yeah, exactly. So somebody's got a good question here. What if we kept track of the rows we swapped? Could you then use the rows from the original matrix? And the answer to that is yes, you could do that. Like, so when we're asking for a basis for a space, there is, as we know, I mean, we learned how to change bases, right? So if you've got a particular space, like in this case, we're in R3, right? It's a 3 by 3 matrix. So we're in R3, and the example I've concocted is both the row space and column space are planes in R3. Okay, so we've got some sort of plane here in R3, right? It goes through the origin. I know it goes through the origin because row spaces and column spaces are subspaces. All subspaces go through the origin. So I know that this is a plane in R3. And once I have that, as you know, if I've got a two-dimensional object, there any two linearly independent vectors that are on the object will form a basis. So this situation here, if you want to look at it this way, this situation here is to take something where you don't know how many vectors you exactly need. You're doing Gaussian elimination. You're finding out which two vectors you need, and then what you're doing is effectively a basis change. So you can, and so let me just draw an R2 example here, just to hopefully make this point here. Here's R2, right? There's a possible basis. That could be a row space of a matrix. That would be a basis for R2, right? This could be a row space, and it'd be a basis for R2. It doesn't matter. which of those two bases I give, they still span the same space. And the row reduction is because we don't know which row swaps we did, we choose them from the end one because we know that these are the is row equivalent, and those are the two ones with the leading variables. Okay, let me just yeah, and so Miles, I would not do that. Like I would just know which I would not keep track of row operations and then make that decision. I would just know which ones to use. Okay, so let me just see if I can answer a couple of other questions about this. So somebody's asking me to do quiz question 2 on the last quiz. Okay, hang on a sec. Quiz, that's quiz 5, question 2. Let me just quickly pull that up. Actually, I've posted the solutions for that quiz. So let me just take a quick look and see what I want to say about that. And then I'll come back to some of the other questions. So, but the solutions are posted, so that should help if you don't get enough out of this. So we're talking about quiz 5. I'm just getting the question up in front of me. Oh, shoot, where did it go? Quiz on file, just a sec. Okay, here's the question. I think I will say something about this because this is an important topic, right? We haven't talked about that too much during this last hour, but this is an important topic where we have the idea of a matrix representing a linear transformation. So let's just write out what this linear transformation is here. And it's looking like this here. Linear transformation. Okay. So always with these questions, you want to capture in your head before starting what's happening. Like, I think it's highly useful to kind of go like this and say, okay, what is the domain? And then I'm looking here, what is the domain? I'm like, oh, it's an R4 vector happening here. R4, that is the domain. And I'm going over here and I'm like, what is this? 1, 2. It's an R2 vector over here. So I'm expecting something that looks like this, x1, x2, x3, x4, just like it's some vector like that to be transformed by this transformation and be over here, y1, y2. That's what it is. Okay, so when the linear transformation is represented like this, it's usually, and in this case, probably the fastest way to do this is to represent the transformation as a matrix. So all linear transformations are representable by matrices. So now I'm gonna want to know, what is the matrix that represents this linear transformation? I know that it's going to be 2 by 4. Right? How do I know that? Because I'm gonna have to multiply here. Like this is gonna have to be 1, 2, 3, 4 entries, 1, 2, 3, 4 entries. I'm gonna be multiplying by something that is 1, 2, 3, 4. I mean, I have to have 4 like that, 4, and then that. So this is gonna be 2 by 4, and then this is my domain, 4 by 1, and then that's gonna have to be equal to my range, 2 by 1. The middle ones have to match. So I can figure out what the dimension of that matrix is right away. So I don't backwards sum stuff up. Like I find it easier better to get my thinking straight. What's the domain? What's the codomain? What's the size of that matrix going to look like? And then I can get the linear transformation by matrix by looking at what happens in the basis vectors. So there's 4 basis vectors in R4. I'm like, what happens to the first one? I see, okay, x1 is 1. I'm like, it's 1, 2. And then I do this for all 4 of them. I say, okay, x2 is 1. I'm getting everything there. X2, no, nothing. Let me copy this thing down, right? Yes, I have. Okay. And then what's the next one? I'm like, x3 is 1. So that's 1, 2. And then x4 is 1, 0, and x4 is 1. Okay. So I'm just basically putting in my input, the 4 standard basis vectors. I'm figuring out what happens according to the rule I got told. Then those things are going in as columns of the matrix. Like that. Okay. As soon as I've got that matrix, then I'm on the standard thing. Found the basis for the null space, find a basis for the range. So to find a basis for the null space, I can augment this if I want, or maybe I don't even need to do that. I can just sort of be imagining that in my head, but I can augment it. I can row reduce. So Gaussian elimination, I get to be here. And then I see that, oh, that's not what I got. Hang on a sec, I'm looking at my answer. I got this. Okay, so I see that there's 2 free variables. Like here's my leading variables, x1 and x4. So I'm like, okay, oh, I've got it augmented. I'm here. And I'm trying to figure out what vectors, if I multiply by this matrix, what vectors give me 0? The collection of all those vectors is the null space. And in this thing, I'm thinking, okay, all vectors where x4 is equal to 0, because that's what this is telling me, x4 is equal to 0. And then x3 is free. That's this guy here, x3. So I call that something S. x2 is free. So I call that something different, T. And then I look at x1 and I'm like x1, and I'm looking at this first row, x1 is minus x3. Then I can write that, what the vectors look like here. X is equal to T times 0, 1, 0, 0 plus S times minus 1, 0, 1, 0. Okay, that's capturing this information here like that. And I immediately can see then the dimension of the null space is 2. And so then the basis, the basis is just those 2 vectors, 0, 1, 0, 0, and minus 1, 0, 1, 0. So there's the basis for the null space. Okay, then I'm looking and I look at this, I look at the row reduced form here, and I'm like, there are 2 linearly independent columns. That's what I'm seeing here. There's 2 linearly independent columns, 1 and 4. So the basis for the range, that is the column space, the basis for the range. So I'm selecting those 2 vectors from here. So that's those 2 vectors, the basis for the range. That guy, 1, 2, oops, 1, 2, and 0, 1. Okay, that's that guy there. Okay, I've actually gone five minutes overtime. I'm going to stay for a little bit more. I'll answer some more questions, but clearly if you've got another class or you're kind of done with this, don't have any other questions, of course, feel free to depart. And I'm not going to say something magical to the rest of the people that are here that you're going to be disadvantaged or anything like that. And I in fact post the recording anyway. So feel free to depart. I'm going to stay maybe about another 15 or 20 minutes, and then I'll have to depart as well. Okay, so let me just now keep going with the questions I've seen. How do we find the null space of the transpose? So, well, one way is just to proceed exactly. So this is now we're trying to find the null space of the transpose. Let's just assume we have some matrix here, 1, 2, 3, 4. Okay, we want to find that and call this A. If we want to find the null space of the transpose, I can simply take the transpose. There, I take the transpose. Then I want to find the null space of that. That's asking for which vectors. For which vectors is this true? That's what it means to be the null space, right? Which vectors in the which vectors when I operated on by the matrix transpose, give me the 0 vector. And so I would just then proceed to go like this, 1, 3, 2, 4, 0, 0. I would do my Gaussian elimination, and I would find out which vectors that is, right? It might be just it might just be the 0 vector, and it might or it might be a line through the origin. So you can just go ahead, Kiara, and just go ahead and do that. Okay. Okay, so there's another thing. How do we find the basis for the range and the null space given a linear mapping in matrix form? Okay, I think we just kind of did that, Tiana. Do you want me to do another one of those? Because that is exactly this question, right? We had a matrix like this. This is, I see her question. We had a matrix like this. We row reduced it. We just found the basis for the null space and the basis for the range. Michael, I see your question. The span of all the roots are the same. I don't understand that question because I don't understand the word roots in that context. So if you're still here, maybe you can just clarify that. Okay, we're not gonna, Sandeli, I see your question. Go over finding the left null space and the right null space. We're forgetting about that. Okay, we're just, I have not asked anything about left or right null space. Okay, so I mean, we are when we've been going like this, ax is equal to 0, we are here on the right null space, right? We're like, which vectors when we multiply on the right do we get 0? I mean, the other way of asking this question is, it would be a different dimension, but we could ask what happens, like what do we multiply on the left in order to get a 0? And so this is a different question, but I don't think I even talked about this in the lecture much, and we're not having that on the midterm, left and right ellipses. No, item Kramer's rule is not on the midterm. We didn't cover Kramer's rule. We're not going to cover Kramer's rule. We don't need that for anything. It's a computational procedure. So that's all. Not. Okay. So hang on. I'm reading Jing Xuan's question. Every linear transformation can be represented in matrix form, but does every linear transformation can be formed by matrix multiplication? Hang on a second. For instance, a linear transformation the linear transformation from a 2x2 matrix to a 2x1 vector. Oh yeah, that's it. So that's a different, and that's still a linear transformation, but you're right. So this is a complicated question. We're not, in fact, I'll just tell you, and I haven't on the midterm, all the vector spaces, and oh, hang on, that might be a lie. Hang on. I'm going to check. I'll actually say something and get myself in trouble. Just a sec. I need to check something here before I say that. With very small exception, and a very small point total, everything is in Rn. There's only a very small, I'll just tell you 2 points out of whatever, 2 points out of some 50 odd points. I can't see the total here. It has anything to do with 2x2, a domain of a 2x2 matrix. This is the vector space of 2x2 matrices. Okay, important topics for the midterm. So that is sort of listed in the midterm topics, but I mean, let's think about I will just answer this. Let's just see what I see as the important topics. Let's just see important. Okay, what sort of things have we done that are big topics that we're going to be using going forward to the applications that we are going to do for the remaining part of the semester, which is really, I mean, once we finish figuring out how to find eigenvalues and eigenvectors, then most of the rest of the course is not new theory. It's about how do we use Gaussian elimination, the knowledge about the subspaces, how to find eigenvalue, and to actually solve some problems. So we won't be really introducing much new material. Okay. Here, let me just tell you about the important topics. Well, we started this review lecture with something, complex numbers. Certainly, I'm going to ask about this. we need to know that is the arithmetic, right? That it's not super complicated stuff on complex numbers, but we want to be able to do basic arithmetic. Okay. Something new that's an important concept was the determinant, right? How to find determinants, what's the property of the determinant, what does it mean when the determinant is 0? So there's that thing. So it's really a key point. Let me just even write it down. If the determinant, so this like this, if the determinant of A is equal to 0, then a to the minus 1 does not exist, right? So if the determinant is 0, the matrix doesn't exist. The matrix inverse doesn't exist. One way to remember this is to think about how to find the determinant of a so we saw, okay, actually, no. So one way to remember this is you should know what is the inverse of a 2x2 matrix. That is 1 over AD minus BC. And then this is like DA and then minus B minus C. We did this, right? Finding the inverse of a 2x2 matrix. Okay. And you'll notice that this thing sitting here is equal to 1 over the determinant of A. So this should clue you in. If you write this down, you think to yourself, oh no, I can't remember if it's invertible, if it's 0 or not 0, right? That could happen. So then what you do is you write this down, and then you're like, oh, look, in the 2x2 case, you're dividing by the determinant. Clearly that can't be 0. So this isn't going to work. This finding this inverse is not going to work if the determinant is 0. Therefore, when the determinant is 0, the inverse doesn't exist. And that scales up to the other size matrices. Okay. So there's that important topics. That's what we were on. Okay, linear transformations. Okay, that's a big topic, right? How to think about given some sort of an operation, either geometrically or by a rule or some other way, like a function definition somehow, and be able to see, is it linear? If it's linear, what is the matrix that performs that operation? How do I capture that linear transformation in a matrix? So that there's and then there's all the like, is this a linear transformation kind of questions. So there's and then I guess coming with that, or maybe, I don't know, there's the basis change. That's change of basis. So if we have vectors, we have to recognize that the coordinates that we have, like 2, 3, like that, is relative to some sort of a standard. So if we should just write it like this, we are thinking that the the coordinates of the vector, like this, coordinates are relative to this basis. They do not have to be. These could be, for example, we could have like this 2, 3 relative to basis B. And somewhere over here, we tell what is basis B, 1, 1, and 2, 3. No, that's a bad idea because it's already used those numbers. Minus 1, 6. Okay. So if we're given a basis like this, we're given a basis, and then we're given a vector relative to this basis, the coordinates of this means 2 times 1, 1 plus 3 times minus 1, 6. Okay, so that is and we want to be able to, if we have a vector represented in this basis, we want to be able to change and represent it in a different basis. So that was an important topic. The one we talked about here quite a bit was the idea of the row space, the column space, the null space, and the null space of the transpose. That's something, the idea that the matrices have these things associated with them, and alongside with that is the rank nullity theorem. That's our major theorem that we've had. We also have seen the fundamental theorem of linear algebra. You do not need to memorize that. I'm not going to ask you to state it, but that has some useful statements there that if you're aware of what they are, you can you sometimes use those in order to solve a problem. Okay, then let's see what else. I guess coming, I maybe should say that here is the idea of orthogonal. Orthogonal matrices or orthonormal set of vectors. Orthogonal. So we have orthogonal We have orthogonal and orthonormal vector sets, and we have orthogonal matrices. So we had that idea. Okay, orthogonal is a huge important thing. We have some of the geometric transformations we talked a lot about, the linear operators that do rotation and reflection and scaling. Sorry, I just see a question popping up in the direct message. Somebody's asking, does this mean I can get 2, 3 from a combination of these two guys? Yes, it does. It's not 2 and 3 of them though. If you wanted to get 2, 3 as a linear combination you want to represent, you wanted 2, 3 to be a linear combination of these, it would be some amount of 1, 1 plus some amount of minus 1, 6. Then you've got 2 equations and 2 unknowns, and you can figure out what those are. Okay, no, James, your question, I'm just scrolling back here. Will we be asked questions about the polynomial vector spaces? No, we didn't talk about that. That is actually way more useful in some ways than the matrix vector space for some applications, but we're not. We're basically going to be in Rn with every now and again an incursion into like M2 by 2, just to sort of see that it's more general than just Rn, but we're not going to ask about the plan. I don't know what Michael's asking. Cross multiplication will be on the midterm. I'm not sure if by that you mean cross product. Then no, I mean, we're not going to use the cross product at all. We don't need the cross product. Yeah, we haven't used the cross product for anything. You can use a cross product and to solve some problems. I'm not recommending that approach because it only works in R3. Okay, so there's that. Okay, just scrolling here. I see another question coming in. The basis for the range. So the basis for the range is the linear combination of the columns, right? That is the basis for the range. Okay, let me just try to make this clear, actually, and this is sort of a bit of confusion. Let me just do like 2, 3 minus 1, 6. Let's multiply this by x1 and x2. Okay, our normal way of doing this would be well, this is the right 2x1 minus x2, right? And 3x1 plus 6x2. Let me write this like this: x1 times 2, 3 plus x2 times minus 1, 6. Okay. So given all vectors in R2, these are all the possible outputs, right? Because I can take some arbitrary x1, x2, and this is the output that I'm going to produce. If I write the multiplication like this, I can see that all possible outputs are linear combinations of the columns. That is the range. This is like all possible outputs. That's the range. And you can see that it's a linear combination, all linear combinations of the 2 columns. If I just write the multiplication out in this way, that means that the range is the same as the column space, because the column space is all linear combinations of the columns. So your answer to your question there is yes. The range is the column space. You should see it in this way. Okay. All right. So Paul, you posted a discussion answer key. Okay, I'm gonna leave that A to Shiki to answer that question in the discussion board, just because I have to pull it up and we're getting close to being out of time, or I'll take a look if I can manage to have that myself. We're sort of running up against time here, so I think I'm gonna call it here. I'm going to yeah, I cannot remember what section that orthogonal vectors are in, but you should know is orthogonal and orthonormal vectors, right? Orthogonal means they're right angles to one another, and orthonormal means they're at right angles and they're of length 1, right? And an orthogonal matrix has orthonormal vectors in it. Orthonormal, the column vectors are orthonormal. Okay. All right. I will be at my office hours tomorrow as well, from 4 to 5. So further questions. And then, of course, I will be there. I expect to be there on Wednesday, and for the midterm. Yep, 4 to 5 tomorrow. Thanks very much, guys, and I apologize for being there, not there in the class today. Bye.